Right, I'll get started. And thank you very much for the lovely introduction, Christian. Yes, that's right. I'm going to be discussing something that I found fascinating to me. It's how animals, so not only humans, but how the rest of the animal kingdom make use of the night sky. And I'm not just talking about using the sun and the moon, which is maybe what we'd expect, how they navigate using these celestial cues, even in the absence of lunar light. So we're going to have a look at just some of the mechanisms that animals do this, some of the studies that have been done. And believe me, I got quite carried away when I was reading it. So I'm going to have to make sure that I keep to time because there's some fantastic studies out there. That really range from birds, as you can see in the silhouettes there, all the way to dung beetles. We'll talk about dung beetles. We'll discuss different mammals and also, of course, sea life as they find their ways navigating and orientating themselves using the night sky. I've also got there in the silhouettes, I've got some elephants, and unfortunately, elephants are not known to navigate by the night sky, but I do have a soft spot for them. And I think, unfortunately, well, elephants are known to have rather poor vision, but I thought that if they could, they would. They're such amazing animals. So they've earned their space on my slides there. So my name is Sally, as I mentioned, and I'm a postdoc at the South African Astronomical Observatory, well, where some of us are located at right now. And I'm working in transient research, so research into transient and cataclysmic variables, mostly using what's called the LSST survey, so the Large Synoptic Sky Telescope, and part of the Rubin Observatory. And I'm not going to talk about any of that today. I'm actually going to go a bit left field. And as I mentioned, I'm going to talk about one of my other loves. Also, part of that work is looking is how we visualize some of the biggest data sets. And in order to do that, we use what I'm investigating is how we can use fully immersive and multi-sensory tools such as planetariums. And that's part of the work that I've been doing. It's hopefully this will actually change. There we go. So I've been working at Zico Planetarium and Digital Dome right here based in Cape Town. There's an image of me trying to look busy in front of some university students. But the Zico Planetarium and Digital Dome is quite unique in the fact that it's one of the few planetaria in the world which not only does it doesn't only do shows for the public, but it also has an active research component as well. So there we try and visualize, get new eyes, new perspectives on some of these large data sets that are coming out of surveys such as Meerkat and the LSST. So all this got me thinking, we can use the planetarium as a very versatile space for other research. And it was during my career in the planetarium that I found out about some very interesting studies that have been done inside the planetarium, using the space for other studies that we might not have thought of before. One of them, including birds in the planetarium. Now, I don't know about you, but working as a planetarian, this kind of image does freak me out a bit. I mean, just thinking about bringing birds into the planetarium and hearing about a study which brought birds into the planetarium. I mean, I got, when I was running one of my shows, I got nervous when a kid brought in a helium balloon. I can only imagine what birds might have done. So during my talk today, we're going to find out why they brought in birds and indeed whether they caused any mess. And that got me thinking, what other animals also have there been studies about in the planetarium? Well, dung beetles as well. And some of the people in the room, or some of the people actually online, may be quite familiar with this study because this study took place right here in South Africa with South African researchers at the Johannesburg Planetarium, or Wits Planetarium, a couple of years back. And we'll go more into detail about this in just a bit. But it's quite an astonishing study and how they use the planetarium to do this research. And indeed, these are just two of the animals that have been shown from these studies to actually navigate by the stars. And once again, not by the moon or the sun, but by the stars themselves, which is an incredible achievement, which we'll get to, or incredible result, which we'll get to towards the end of the talk. So with animals itself, the studies that have been done into using, to looking at how animals use these celestial cues, we understand that animals do use these celestial cues. The question is though now, how? So how are they navigating? What are those orientation strategies? And we'll have a look at a few of them. That's an ongoing research and something that's hotly debated in certain studies. And what I really do recommend doing is a lot of my talk, a lot of my slides today are based on this research, this paper, how animals, or this review rather, how animals follow the stars. And I really recommend taking a look at Foster et al. 2017 to read up more about what I'm saying today. So before we get into looking at animal navigation, we can't go any further without looking at, well, what we can relate to, the human kingdom. And humans have for centuries, and I really mean centuries, used the stars in order to navigate their way around the world. And this is, I love this image. It's one of the images I found. It's very difficult to actually track down a good quality version of this. I found this version on Etsy by Minsky Designs, and you can buy it for 500 Rand if you want to. But this one is, it's a beautiful, this is a colorized version, but it's a beautiful display of beautiful old illustration from the 1900s, mid-1900s, or sorry, rather the mid-19th century, that features not only, well, ships that are navigating the seas, but also Table Mountain in the background, along with the Milky Way in the background as well. Quite a beautiful image. So this got me thinking, where does celestial navigation date back to? And we can look no further than looking at something that's called the mechanism of Antikythera. And I did practice that word quite a few times, but Antikythera, I can probably be corrected by people in the audience, but this is one of the earliest known examples of celestial mechanism that's believed to be used for celestial navigation. So this device, and it's been in the news, I don't know if people have read about it, but it was discovered in a wreckage in 1900. And it's made up of 3 corroded bronze plates that you can see in the image there, and featuring some of the earliest known examples of gears and wheels. It really is a phenomenal discovery that they made. And it's believed to be one of the earliest, the world's first analog computer. And they believe that it was possibly used for celestial navigation. So it was able to imitate the movements of celestial bodies. And that's right back to BC times, 150 to 100 BC. So really humans have been using the stars for hundreds upon hundreds of years. Now, in this next slide, I'm going to do my best to describe celestial navigation. And I will freely admit, when I was trying to do up these slides, I did Google celestial navigation for dummies. But so excuse me, if I probably have some experts in the room here. Feel free to correct me. But in order to start, just to give you a bit of a background, I'm sure this is preaching to the converted here, but for those who are not familiar with our celestial sphere, we've got an Earth, and surrounding the Earth, we've got this other sphere we call the celestial sphere, on which all the stars are projected. Now, like we have a North Pole and a South Pole, we've got this projected onto the celestial sphere, a celestial North Pole, and a celestial South sphere. A South Pole rather. Like we have an equator, we also have a celestial equator. So as the Earth rotates, these stars appear to move around on the sphere, or rather the sphere moves around us. And because these stars or objects are projected onto the surface, each of them can be located using their own declination or coordinates, with declination and right ascension. But what this means also is that the stars in our night sky, when we observe them outside, we see these celestial poles as remaining still in our night skies. So with all the stars rotating around them. So this is the case in the Northern Hemisphere. We've got the North Pole, which is represented by a star, Polaris, and then the celestial South Pole. We've got a bit of an obscure region that can be found using the Southern Cross. So that's just a bit of a background. But now, how did we use this to do celestial navigation at sea? Well, for me, I've always seen these beautiful instruments. And for example, in the lower image there, you see a sextant. And I've actually got in the next slide how a sextant is actually used to try and detect or try and measure these angles. So I found this quite an interesting. It does, this is a GIF, so hopefully it'll loop back down to 1. But in order to do celestial navigation at sea, and as it says there, in order to locate, sailors to locate, or navigators rather at sea, to locate themselves on the ocean, they can determine their position by a number of different methods that can use either the sun, the moon, or planets. And by using these, by using sextants, or by using such things like precise timepieces, as well as almanacs, we are able then to determine where you are in the ocean. So your latitude and longitude. And this just goes, you can see in this diagram, we've got 3 different methods that you can use. By measuring, by using your device such as a sextant, you can measure this distance between the horizon and a specific star. In this case, they've used the North Star as it's moving past your local meridian, so the highest point on its path through the skies. Using that angle, you can then get your measured, as it says there, you can get your latitude. Now, you can either use the North Star or a number of about 58 well-known navigational bright stars. So in order to find the latitude, that was pretty straightforward for sailors. But to find the longitude, on the other hand, that was always a little bit more involved. Because now, not only do we need to know the angle, a good estimate, or we need to measure the angle, we also needed to have a very precise time as well. And that was when marine chronometers started to come into play as well. So a marine chronometer is a very precise time device that was used to keep very steady track on ships of Greenwich Meridian time. And by measuring the time and comparing the time at Greenwich Meridian to your time, local time on the ship, you could then work out your longitude, because we know 1 hour is equivalent to 15 degrees as you travel across. This is all very straight, very simplified, dumbed down, but that was one method that they could use to find longitude. in order to find your local, in order to find that time and also to find that longitude, you could use, as they show in the bottom image there, and they talk about finding local noon with a sextant. If you look for the sun as it crosses your local meridian, you could then calculate, use that to also calculate along with your very precise time. You could use that to find your longitude. If you don't have your chronometer, there is another method that you could use, the lunar distance method, which is illustrated in that middle diagram there. And in order to calculate that, they use the moon and the distance from the moon and the sun. And that's a very good method that's still being used roughly today mostly by hobbyists, but also it's encouraged to keep up at sea in case you don't have these highly precise time devices. Modern times, well, now we use GPS satellites as well as sextants and some of our modern equipment. They still train on sextants, but heavily also rely on GPS as well. So that's a quick bash at celestial navigation. But I also just want to take this opportunity to look at some of the beautiful instruments, and really the slide is just celebrating some of these beautiful images as well, and these beautiful instruments that were used from the 1600s, around the 1600s. I mean, talking about horary quadrants, which were used to find time by measuring the sun's altitude, nocturnal, as well as mariners' astrolabes, and compasses. Now, I'm not going to talk on anything more. I just like to appreciate these images. And I sometimes wish that some of the work we do today could be portrayed in such beautiful illustrations. So we've got, so that was for humans. I've illustrated over the last couple of slides how humans then can use the sun, can use the moon, can use bright stars to find our way, and these beautiful instruments to find our way to different locations using the stars. But as I mentioned, we're not the only ones. And in fact, animals also make use of these navigation techniques. So I was checking around for good comics about navigation and celestial navigation, and settled on this one. Now, the question is, we hear about animals making these wonderful migrations across vast distances that are amazingly accurate. They're able to find their way back to breeding sites. But the question is, have you ever asked how they do that? How do they navigate across open waters in either cloudy skies or when there is no moon? How do they keep going? And there are some amazing cases of, for example, I'm going to talk about birds for a second. We're going to start off by talking about the Arctic tern. So the Arctic tern holds a record for having some of the longest journeys, longest migrations. It'll move all the way, it'll fly all the way from the Arctic Circle all the way down to the Antarctic. And it'll make a return journey in a year that covers about 30,000 kilometers. So these Arctic terns, they live to about 30 years. So if you add up all of these journeys, you can see how that is basically the distance to the moon and back again, a couple of times. So it is an absolutely amazing adaptation that these birds must have in order to be able to navigate that distance. But they're not the only one. There's many other birds that can do this. And I promise you this is not a bird talk, although I could go on about birds for quite a while. But there's another absolutely astonishing bird, and that is the bar-tailed godwit. And isn't he a handsome bird there? But the bar-tailed godwit, it holds the record itself for the longest journey without stopping. And I've got an image of that here. So the bar-tailed godwit will migrate from the Alaskan tundra all the way down to Australasia. This is some 11,000 kilometers without stopping once in 9 days, which is an absolutely astonishing feat when you consider and wonder about how they do that. So they do that regardless of cloudy conditions. They do this even in with no moon and such. So you can see they make the journey from Alaska down to where they have their breeding areas, their breeding grounds in Alaska. They move down to New Zealand where their feeding grounds are. I bet they're pretty hungry by then. Then they move off to Australia and up the coast where they have their resting and breeding sites. So this is not only these incredible migrations are shown by these birds. These are just 2 birds, but not only birds, they're also these migrations. Incredible migrations are also shared by whales and seals and all sorts of other animals, which we'll go into a bit more detail. So over the next couple of slides, I'll be now looking at how birds in general are able to make these massive migrations. How do they navigate? So here's a basic diagram that shows some of the ways in which these animals, and in this case, birds, will migrate. And I mentioned migration, navigation, and birds, but this can also apply to other animals. And as we go along, I'll talk about some other animals' cases as well. We've got, as an example, this is another example I just remembered, the stork as well will migrate all the way from Europe to Africa. And on its journey, they not only know the route, but they'll be able to detect swarms of locusts to feed on before humans even know this. So there's studies researching that as well. So just to go over some of the different techniques, we'll start off with odor map. I'm not going to stay on odor map. We want to get to the stars. So just out of interest, one of the navigational ways in which these birds do navigate, some birds navigate, is to use different smells that are brought upon by winds. And they're able to map this, they're able to memorize this, and map their way out by detecting these smells. Another way that I'd like to just speak on for a bit is by using some birds are able to navigate, and some animals as well are able to navigate using the magnetic field of the Earth, and rather the changing magnetic field of the Earth. And this is either by memorizing certain areas, magnetic disturbances, which they can then fly around, by creating these magnetic maps, or by using a magnetic sense, which I'll be discussing in the next slide. They have these inner GPS, these magnetic compasses, which they can then use to detect the magnetic field, which is quite an astonishing feat. And the way I love these studies, the way they've detected some of these things is back in the kind of 50s and 60s and 70s. They would take birds, and in this particular study, they took nocturnal migrants, or in this case, robins, and they put them inside a cage. They put them inside a cage, and then around the cage, they had wire coils, which they injected a low electric current in it. And by doing that, researchers then could alter the magnetic field around the cage. And from doing this, they were able to detect the birds were able to, let's just check. Oh, well, I'll stop talking then. No, we're just getting onto the good parts.
We can hear you.
Okay, so let's change to devs. Okay. Is everyone able to still hear me? Can you just type in the chat? Okay, great. We've just we've lost. We went into load shedding here, so we've just lost our projector. But okay, well, I'll carry on talking about this experiment. So we're still sharing, so that's great. So with this robins inside this cage, by altering the magnetic field, they were able to discover that these birds were reacting to the change in magnetic field. They had some magnetic sense. And that was really the start of these observations. Of course, they can do that with robins, but when you look at things like whales, well, it's a bit more difficult to construct this massive cage. So they have other techniques, which we'll get into in just a bit. So, excellent. We've got a screen. So how then do these animals manage to navigate using the magnetic field? And let's see if we can change. There we go. So the leading theory, or what's been researched and belief, is that there's actually a sense that these animals, well, a lot of animals in the animal kingdom have this sense that's able to identify or work with the magnetic field, and we call this sense a magnetoreception. And this has been found, and this is just a taxonomy of a few different animals that have been exhibited this sense, this ability to navigate or orientate by magnetic fields. So in essence, what they're doing is they're using the Earth's magnetic field as an internal GPS system. And in certain cases, they use the magnetic field to orientate themselves, also to navigate, but also in some animals, it's been shown that they can use it as a magnetic map as well, which is what I was discussing a bit earlier. So they memorize these routes across the Earth. What causes this magnetoreception? Well, there's a lot of research into this, and the two leading theories at the moment is, the first one is a mineral we call magnetite, and this is in essence crystals that are in essence rotating, rapidly rotating magnets, just to dumb it down quite a bit. That's one of the theories. And in fact, these clusters of these little iron clusters have been found in the beaks of certain birds, for example. So in homing pigeons or in domestic hens. So they believe that that might be the reason why, well, in homing pigeons, maybe that's also why they respond when they're homing, why they respond to the magnetic field. Another theory that that causes this, another belief that, or theory that causes this magnetic reception is a chemical reaction. And researching this was tough for me because I haven't done biology in a long time. So a chemical reaction to do with proteins, and this protein is written there, it's a cryptochrome protein, which causes these, the sensitivity to the magnetic fields. And this cryptochrome, as it shows there, has been observed or studied in various animals. And I'm going to go just talk a little bit about the different animals that you see there. Firstly, one of my favorite discoveries was that they used this to detect, to study the giant sea slug. What researchers found is that the giant sea slug will actually align itself along the north-south axis. Sorry, rather will orientate its body between north and east just before the moon rises, prior to a full moon, which is quite an amazing feat. So once again, by building these cages, by manipulating the magnetic fields, they were able to then detect that these slugs were aligning themselves according to magnetic field. Now, this cryptochrome has also been detected in, for example, the honeybee, and we'll get into the honeybee in just a bit, but also homing pigeons, as well as other animals there like bats. Now, bats are also known to use echolocation, but it's been found that they also use magnetic maps and magnetic fields to orientate and navigate. And not only that, but bats have an extra feature where they've been found to use the rising or setting sun to orientate this, where that is in relation, at least to orientate themselves as they take off and then navigate by the magnetic fields. Now, the one study there that I want to go on a little bit more about is sea turtles. Now, sea turtles are incredible. Another migrator that migrates past different distances. They can swim for tens of thousands of kilometers and come back to the same breeding site or the same site where they were born decades earlier. And it's believed that they not only use they're able to identify both the orientation, the magnetic field, as well as the inclination, the intensity of the magnetic field, as well as the inclination of the magnetic field, in order to create these magnetic field maps or these magnetic maps that allow them to return to these breeding sites. Really quite incredible. But I said I'd mentioned about the whale, and we've got an image of the humpback whales. Now, whales are pretty special. Once again, also migrate these vast different distances. Now, a study was done with humpback whales, and they were found, a study done by Horton et al. And he mapped out, he put kind of traces on these traces to measure where the whales had gone on these whales as they moved out from Brazil down to the Antarctic Circle and over multiple years. So now what they found is that and you can see in the image there, that these whales were tracing out incredibly straight trails despite going through storms. So they weren't knocked out by storms, they weren't knocked out by uncertain sea conditions, they were still navigating on these routes. And the researchers put it down to not only, it's actually a combination of both magnetic fields, a magnetic compass, as well as a sun compass as well. So they use, and what they theorize is that these whales are possibly using where the sun is in relation to the magnetic field to navigate these extremely long distances with such amazing precision. But on the other hand, so these whales, they can use these magnetic compasses. On the other hand, whales also illustrate some of the negative features of having these internal GPS magnetic compasses. And that's because, they found in a study done in a couple of years back, they started looking at whale strandings. Now, when whales strand or dolphins strand, it's usually, a lot of the times it's due to the marine life being maybe hit by passing vessels or illnesses, diseases. In the case of these strandings, they found, looking at 57 years of strandings, they identified whales that had been stranded that had not been ill, they had no injury. So the question was, why were they being stranded? And they put it down to not being able to, coming closer to shore, making a mistake and getting stranded as they lost the navigational sense. So why? Well, these researchers then compared these 37 years of strandings to records of solar storms. And what they found is that there was a massive correlation between solar storm and high solar activity, as well as these whale strandings. So it's quite interesting. Unfortunately, if you Google Horton et al., you'll be able to find some of those studies, or rather not Horton et al. If you just Google whales and solar storms, unfortunately, I don't have the papers here. But what they discovered then was the whales were not being stranded due to shifts in the magnetic field. Rather, they were being stranded because during these storms, you get these bursts of radio frequency radiation. And that was interfering with the magnetic receptors inside the whales. And that was basically blinding the whales on their navigation routes. So whales, pretty amazing what's happening, the hidden world around us. And it really is a hidden world because they've tried to detect this magnetoreception in humans. And although we have that protein compound that other animals have, so we have the ability, but we don't have magnetic reception. So we can't detect magnetic fields as far as we know. At least there's no evidence to prove otherwise. So we've talked about magnetic fields, we've talked about star compasses and odor maps, but what about sun compasses? Well, some compasses, some birds are known to use the sun, have to navigate using the sun. Some birds also, as I mentioned earlier, we've got bats, which also use the rising and setting sun to orientate themselves before they navigate using the magnetic compass. We also have polarization. So the sun polarizes our skies. We have linearly polarized light lattices around us, and animals have been found to navigate using that polarized light. I won't go into too much detail there. So what we have found is that bees are known to use the sun, and in a very interesting way. So bees are known to communicate via dance. They'll dance to communicate with the rest of their colony members. And they do a very special dance which involves the sun. It's called the waggle dance. And this is an example of what they're doing. And what it shows you there is this astonishing thing is the distance of that little squiggle indicates how far it is to the nearest to their flower. And the angle at which the wiggle is compared to how your how their colony, their nest is standing, that tells you in what direction it is using the direction of the sun. So what the bee has done is gone outside, seen his flower, and uses the angle from the sun to that flower, uses that angle and brings it back into its wiggle dance. So they know that which direction is up in the nest, and the wiggle dance will then be slightly angled away from the up direction, and that angle is then used outside compared to the sun to find their flower. Quite an astonishing adaptation by bees. So I've talked all about these different compasses, and really what we want to get into now is star compasses. How do these animals navigate if they're not navigating using magnetic fields, or in addition to magnetic fields, if they're not using the sun or the moon, how do they use the stars? And this has been shown over the next couple of slides. Sorry, I think someone needs to turn off someone needs to mute. Yeah, sounds right. Okay. So over the next couple of slides, we're going to be looking at some studies that have been done to show how animals not only navigate and orientate, but how they do that. Some of the orientation or navigation strategies that they use. Okay. So we turn to the birds in the planetarium. And this picture still freaks me out a little bit. But this time, we're not going to stop with this image. A study was conducted by Emlet et al. Back in the 60s and 70s, 50s, 60s, and 70s, using the North American indigo bunting. And that beautiful bird over there. So sorry, we still got a few more birds coming. And this is a well-known North American bird. It migrates as well. And what Emlyn did is he grabbed a few of these birds while they were migrating south for the winter. So it was on their autumn migration. And what he did is he went into the planetarium and built funnels for them. So much like we had earlier to detect magnetic fields, now this researcher is building a funnel device in which he put the birds. So no mess inside the planetarium, thankfully. But as you can see there in the diagram, it had a bit of a stamp at the bottom, the bird and a outside cardboard funnel with blotting paper on it and a wire screen top so that the bird could not escape. A bit sad, really. So what happened is that as the bird took off, depending on what it saw above it, it would take off in a certain direction. And they were able to track that direction using the direction of the stamped little feet on the funnel. So here's an inside image taken from the Longway Planetarium. And you can see he had a couple of these funnels set up. So the first thing that he did in these tests, this research, is he first seen if the bird's biological time clock had anything to do with it. And what he did is he immediately set the stars to another night, another time, to see if that would change the orientation of the birds. But it didn't. The birds were able to very quickly adapt, which meant the birds were using something else to navigate by. Next, what he did is he then started, and they have these beautiful, in these planetariums, these beautiful optomechanical machines. What he started to do was blocking out some of the light from some of these star asterisms. Other star groups, the birds still managed to find their way until he started blocking out light from stars that were within 35 degrees of the North Celestial Pole. And by doing that, at that point, the birds suddenly lost control. They weren't able to navigate. They were going in all different directions. So from this study, and since then, many other studies have been done with other animals, it's now believed that birds are able to navigate and orientate themselves by using the celestial poles. I haven't yet heard of this test being done in the southern areas, but in the southern hemisphere. But certainly in the northern hemisphere, using Polaris, or at least using that center of rotation. So we know that the birds are using that center of rotation, but the question is, are they using asterisms around it? In addition, that's on ongoing research. So birds have been shown to use that center of rotation, but what about other animals? Seals have been shown to use bright stars, so what's called lodestars, to navigate by. And in order to find this, a study looked, first of all, they asked the questions, can seals detect bright stars? And that's in that first paper, How a Harbor Seal Sees the Night Sky. In the second paper, in the second study, they looked at, we'll get onto that. So this first study, what they did is they got a seal to look through a tube, which they called a seal tube. Very creative, but they called it a seal tube. And they got the seals to basically remove their faces, their heads from that tube if they saw a bright object. And the seals were successfully able to do this when they spotted Sirius and Venus. They repeated the experiment and they discovered that seals were able to recognize stars that were brighter than 4.4 magnitude, around 4.4. So they were able then to detect that seals could detect these bright stars. So could they, then the next study they did is they asked, can they navigate by these bright stars? And in order to do that, they set up a floating planetarium, which the seals were located on. And the researchers then pointed out bright stars using a laser. And they trained the seals to go to that bright star and give them a reward. Then they switched off the laser, changed the orientation of the planetarium, and the seals were still able to detect that bright star even in the new orientation. There are some uncertainties with this study, but it's a very interesting result. Moths have also been found to be able to detect. So whereas birds can detect by rotating stars, the center of rotation, seals detect by these, navigate by these bright lodestars. Moths have been found had a very interesting reaction. They, unlike the others, they were found to, when they were navigating by the stars, they were actually found to start to drift. And they would drift, they couldn't navigate, they were found they couldn't navigate by the rotation of the stars or by bright stars, but these researchers in the study found that they were drifting towards a region of the night sky that was 95 degrees away from the North Celestial Pole. They were doing the study in the northern hemisphere. And that correlates to or corresponds to an area of the Milky Way that's between Sagittarius and Scorpius, which is the center of the Milky Way, where there is a greater illumination. So it's possible, although this is still research that's being done, it's possible that moths are able to detect gradients of light intensity across the night sky and navigate. Of course, when there's a moon out, they'll navigate via the moon. In the absence of the moon, possibly this is the way they navigate. Which brings me to another insect. And this is the last, pretty much the last, well, insect that I'm going to be discussing. And that's the dung beetle. So this is actually one of my, you can see I've built up to this. This is one of my favorite studies. Dung beetles in the planetarium. And I was quite surprised to find that this took place right here in South Africa. And the study, I mean, of course, the dung beetles, local dung beetles, but it took place in Johannesburg Planetarium. Now, dung beetles, when they're rolling their balls, there's intense competition at the dung heap. So they'll want to, unlike the other animals I've discussed, they're not migrating. They travel very short distances, but they travel in very straight lines away from this dung heap. So researchers were wondering how they navigated away without redirecting themselves back. How did they navigate and orientate themselves away from this dung heap? And that actually led to the discovery that they were navigating by not the stars, but the Milky Way itself. And this was a study done This was a study done by Dak et al. In 2013. And it was actually an accidental discovery. These researchers in Wits University, as well as Lund University in Sweden, were actually trying to detect whether dung beetles find it cooler to be on top of dung balls. And that's actually a bit of an aside, but in that experiment, what they did is they put little boots on the dung beetles. And because dung beetles, if you've ever seen them, they'll jump onto dung balls and they might do a little dance on side. And they wondered if that was because of the heat of the ground. And they found that the dung beetles who had these little booties on, they were less likely to go onto the dung balls than those who didn't. So they had theories that that could possibly be the case. That also led them to look at how polarized light affected dung beetles in their travel. And for that reason, they put on these little caps. So not unfortunately the top hats as you saw in the previous image, but these little cardboard cutouts. And that led them to the discovery that when they put the little hats on these dung beetles, they weren't nearly as accurate in their trajectories, their pathways. So that got them thinking, and that's when they started doing these studies. They built a big arena outside with a 1 meter wall. They started the dung beetles in the center and sent them out and timed how long it took these dung beetles to roll their balls to the outside. And what they found, and then they put the cap on, took the cap off. What they found is that in an uncovered sky, yes, it would take them a certain amount of time, relatively straight lines. When they put the cap on, they found that. So they decided, okay, well, maybe they're using terrestrial cues. So what they then did is they made the arena higher, and they increased the wall height to 2 meters. And there's a story about now they didn't have they weren't watching, their camera equipment wasn't watching above. So instead of that, they didn't want any kind of outside influence that might influence the beetles. So they had a sort of gutter around the edge. And they talk about how in their paper, the dung beetles, when they got to the edge, it would make an audible thump as it got. So they were able to, and I feel so sorry for these birds and these dung beetles, but they were able to, this audible thump, they were able to detect when the dung beetles had reached the outside. And once they got to that audible thump, and the second they found, still, even with the higher walls, they still had the same result. Didn't change. The next step, they wanted to see what exactly, so they knew that dung beetles now were navigating by the stars, but what about the stars were they navigating by? And I'll get back to that just in a bit. So then they brought them inside the planetarium. They brought them to Johannesburg Planetarium, where they set up this huge arena and repeated the same experiments. And they repeated the experiments for a full night, for a full starry sky, for a starry sky without the Milky Way, with just the Milky Way, with bright stars, with dim stars, and with a dark sky totally. And they found, from doing all these experiments, they discovered that the dung beetles responded or weren't able to navigate when either there was a dark sky or when there wasn't a Milky Way. So they could still navigate even if there was no other stars and just the Milky Way. They were still able to create these short distances, these relatively straight lines. But without the Milky Way, they suddenly lost their navigational skills. Now, this brings me to, in order to understand why they were using the Milky Way, we've got to understand why insects, actually how they see. And insects have compound eyes. So with dung beetles, well, usually for us, when we're looking at the stars, or stars tend to subtend maybe 0.1 arcsecond in the night sky. With dung beetles, because of their compound eyes, their low resolution eyesight, they can only see to a resolution of about 4 degrees, which means the sky that they're looking at is Milky Way that they're looking at is rather a gradient rather than individual stars like the other animals that we've seen. And this is similar perhaps to other insects. So the theory is that the dung beetles are actually looking towards these gradient of light. You can see there's a brighter spot there, and that corresponds to the region around the Southern Cross. And it's believed that dung beetles use this change, this varying gradient, in order to navigate. So a very, very interesting result. And you can also find out more about that in Foster et al. 2017. So the question is, and I'm now coming, unfortunately, to the end, almost to the end of my talk, but we have these beautiful skies. Animals are known to navigate by all different mechanisms, magnetic fields, or by polarized light, or by changing patterns of polarized light, or by celestial compasses. an interesting result here in the bird experiment, birds are navigating by these center rotations. What the researcher next did after he brought the birds into the planetarium, he actually raised some birds in the planetarium and then reset the axis of rotation away from the North Star to Betelgeuse. And the birds then reorientated themselves to Betelgeuse. So it was a very interesting addition, a very interesting result. But now what happens when we start seeing skies like this? And it's a very sobering thought. So this is another, unfortunately, light pollution doesn't only have issues for human navigation, it also has dire consequences for animal navigation. And this is in addition to polarized light as well, which is another issue that gets heavily affected by urban skylight. So this is a good paper to read up on about Kaibe et al. Goes into lunar skylight polarization, how that changes as you go, and they did a study in Berlin, and how it changes from rural areas where it's about 70 to 80% into urban centers of Berlin, which is 11%. And what's worse is that this is then carried on by the cold air into the rural areas. So of course, animals are going to get affected by this. And then also we can't help but think, what about satellites, strings of satellite? How would these affect birds on these endless navigations across the sea when they suddenly see these other stars that are moving? Well, this is areas of research that is being done. So animals navigate by different manners, and I've just gone into some of the studies. It's really fascinating, and I'd love to read up more about these different studies. In fact, it comes down to the fact that we know that birds are now navigating. It's an incredible result that we know birds, animals, mammals are navigating by the stars. The question now in the research is how? How are they navigating by these stars? And what we need to do is bring more animals into the planetarium. We need to test more things, maybe not an elephant, unfortunately, but we can test on smaller animals, and that's certainly where research is going. So thank you very much. I haven't gone too far over time.
Okay, very interesting presentation, and I'm sure there are questions.
I'm not sure how much I can answer the questions, but it's just a fascinating area. Let's see. Oh, we've got some amazing things. Thank you very much. I hope you enjoyed yourself. Oh, this is just a slide advertising the GA 2024. I thought I'd add that next year, but I'm sure we'll have another talk on that. Yeah, are there any other questions?
I have one.
Yes.
I'm not sure you had an answer, but you,
Oh,
you said, if I remember correctly, that the sea, the great like oriented between north,
yes.
south, and then the full moon comes. Why?
No, I wish I remember, but I can't remember. Oh, it was one of these older studies. So, but love to know why. I just, all I can think of is these researchers sitting in a lab with these sea slugs and analyzing how and trying to adjust how they're positioning. But I can't. I'm going to have to come back to you on that.
No, but that's fine. I was just wondering.
Yeah, no, but it's a very good question, because they must do it for a reason. But why? All the other animals did it.
So I've got a question.
Yes.
Can you hear me okay?
Yes, Ketchel. That's Ketchel, right?
It is, yes. So now I've heard that, sheep, when you see them on a mountainside, they follow the contour lines of the mountain. But I've heard that sheep and cows, that they actually are orientating themselves along magnetic lines. Now, I don't know how true it can be. But I've also heard that there's sort of weak evidence that humans also can detect, you know, if you put them in a dark room, there's been experiments and, you know, they can sort of detect the cardinal points at least, but I'm not sure if any of this is true. But my real question is, what does it feel like to feel a magnetic line? I mean, we know what it feels like to feel heat or to hear something. I mean, what must it feel like to have a magnetic map?
It's a fascinating question, and I mean, actually, just to address some of the sheep aligning. I was on a drive to Greyton a couple of weekends ago, and all the sheep were facing one direction, and I can't help that just reminded me of that moment. Why? Maybe along the magnetic field lines.
No, I can answer that question, because I was brought up in sheep farming territory, and usually sheep's main motivation is to get out of the wind.
Oh, no, but it was just one group of sheep. The next field, they were all different directions. So I don't know. It was. But no, there was a study done, and now that you mention it, so I mentioned that humans, we don't have this sense, this magnetic reception sense, but we do have that protein. There has been some studies done that brain waves do alter in magnetic fields, but I mean that's there have been some studies. That's why it's kind of an uncertain area of research at the moment. But yeah, I don't know. It's an amazing thought that there is something like a magnetic field, and animals all have the sense that we don't have, and it is quite a it makes you think of the bigger picture really a bit more.
Can I add quickly to Ketchell's thing about the sheep or whatever? So yes. farmers will tell you that, I mean, they obviously will observe the sheep's behavior the best, because in the Karoo, the camps are massive. You know, they are several square, they kilometers away. So if you need to go and collect the sheep from a camp, they only observe the wind direction. So sheep always graze upwind. So, and if the wind's been blowing for 5 days, the sheep will be near the end of the camp on the upwind side. So it's a very simple.
Okay. I'm gonna keep an eye on next time I go to Greyton. I'm gonna keep an eye on this sheep field and see if I can sense the winds. Yes.
Just speak to a farmer. They'll tell you all the secrets.
Yes. Thanks.
I have a tricky question.
Oh no.
It's not about an animal.
Okay, yes.
But if I saw that correctly on the slide where you had all these animals using magnetic reception, there was also pea.
There was, sorry?
I thought there was a pea.
And that's the interesting thing. I forgot even to mention that not only animals, but plants as well have, although I didn't read up into that in any more detail, maybe when I next give a talk on a plant's guide to the night sky, or but yeah, no, plants have been, there is some research into plants having this magnetic reception sense. So
absolutely amazing.
Yeah. Anyway. So yes, sunflowers, and so they have this solar compass, like, well, no, they don't orientate by. Yes, they orientate by solar, but these studies, I mean, I'd have to read up more about it, but I mean, it appears that they also have some sort of magnetic sense, which is fascinating. Yeah. Yeah. Okay.